Welcome to part two of our carbon cycle presentation with Ms. Chang. So part one talked about the four different spheres as well as the carbon reservoirs found within them. So now this part of the presentation is going to be about biogeochemical cycles. What the heck are they? So here's our definition. It refers to the cycling of matter such as carbon, water, nitrogen through biotic and abiotic factors within the four spheres. So what that just means is that abiding to the law of conservation of matter is constant. The amount of matter on Earth is constant. Three, two, one, go. All right, welcome to part two of the carbon cycle presentation with Ms. Chang. So part one, we talked about the four different spheres and the various carbon reservoirs that are found within the four spheres, as well as the form the carbon takes in each of the four spheres. So now we're going to talk about biogeochemical cycles. And then this long word, what exactly does it mean? So it refers to the cycling of matter such as carbon, water, and nitrogen through biotic and abiotic factors within the four spheres. So when we talk about carbon in the four spheres, with the previous slides, we gave you a fixed number such as 800 gigatons of carbon within the atmosphere. But as you might already know, the amount of carbon within the atmosphere is not constant. There are things happening such as photosynthesis and respiration that occur that will change the amount of carbon in the atmosphere. And we already know that humans change the amount of carbon in the atmosphere as well. So just like how we have the water cycle, it cycles through the atmosphere, geosphere, biosphere, and so on, that carbon as well as nitrogen will do the cycling. So we're going to focus on just carbon cycles. So let's go ahead and introduce the 7 different biogeochemical cycles that we will discuss in this slide. So the first one is going to be photosynthesis, respiration, death and decomposition, land use change, fossil fuel combustion, sedimentation and rock formation, and the air-sea gas exchange. One thing to note about these processes is that you have a differentiation between natural and man-made cycles. So here in this green box here, so most biogeochemical cycles are biogenic, meaning that they're naturally occurring sources of carbon. So for example, respiration adds CO2 to the atmosphere, but it's not a terrible thing because of the fact that naturally photosynthesis cycles it back to the biosphere and it has a nice balance going between them. However, some processes such as the land use change and fossil fuel combustion are non-biogenic sources, also known as anthropogenic or man-made sources. So whenever humans intervene, that changes what's going on because it's a very delicate balancing act. And we want to discuss more of that towards the end of our slides. So let's go ahead and get started. So the process we're going to focus here is photosynthesis. So most of you guys are familiar with this. It has the equation of carbon dioxide reacting with water and sunlight to produce glucose as well as oxygen. And then producers, which are your plants that use photosynthesis, make their own food by removing carbon dioxide from the atmosphere and turning it into sugar. So sugar is stored in plants not only as a food source, but it's used to make various organic compounds such as cellulose and gives plants their structures and rigidity. And like we mentioned in part one, sugar can actually be used to make other organic compounds such as proteins and fats and so on. So the plants have really cool abilities to change one simple chemical compound into very complex things. So the organic molecules are rich in energy, are referred to as biomass, carbon stored within the biosphere. So as mentioned before, most of our biomass is going to be stored in plants. So carbon is stored in the biosphere as biomass. And the two spheres interacting for this process is carbon coming from the atmosphere, being removed from the atmosphere, and going into the biosphere. Our second process is respiration. So here we have a similar picture. It shows that photosynthesis is moving carbon into the plant, but also shows the plant releasing CO2 through respiration, and it shows you all these animals that, although they do not go through photosynthesis, also release CO2 through respiration, as well as bacteria and worms. So respiration's chemical formula is the same as photosynthesis, except you flip it over backwards. So you take the glucose, which is your sugar, and then you breathe in oxygen, and that process will produce CO2 and water vapor as well as energy. So all organisms in the biosphere consume sugar from their food and undergo cellular respiration to produce energy. So that's the main objective of respiration, also known as cellular respiration, is to release the energy that is stored within the chemical bonds of glucose, and in the process, it releases CO2 into the atmosphere. So the direction of movement is from the biosphere and the atmosphere. So respiration and photosynthesis has a beautiful balancing act where there's actually more photosynthesis occurring than respiration. So plants are carbon sinks, and it removes the excess CO2 from respiration. So we're not increasing CO2 on Earth just by breathing it out. So plants help make the air cleaner. So the next part is decomposition. So you can't talk about life without death. So when organisms die, other organisms will consume the remains and introduce biomass into the geosphere. So what we mean by that is whenever a consumer eats another organism, it's going to create poop. So for example, when you eat chicken, you're going to create feces. Feces has a lot of carbon in it, and it's actually very energy rich. You can burn feces for energy. Another example is that the bacteria and fungi, which is all around us, will also consume us. And then not only does it produce feces, when it breaks down something like a tree, it produces humus. So humus might be something you've not heard of, maybe in horticulture class if you're going to take that in the future. But humus is a key component of soil. So if you look at dirt, you might see that some of it looks like bark. It's because that's made from dead trees, and that is very nutrient dense. So with decomposition, the majority of it is from the biosphere to the geosphere, returning carbon back to the earth. So that's the cycle of life going on here. However, a small portion of biomass is also going to be converted into gases such as methane during the decomposition process. However, for the sake of simplicity, we're just going to say that decomposition moves carbon from the biosphere to the geosphere. So land use change is different from the first 3 processes we talked about, because the first 3 are biogenic or natural cycles that happen for millions, hundreds of millions of years before humans even set foot on Earth. And then humans are a special animal species. So what makes us different than other organisms is that we build permanent dwellings. We build towns, we make roads, and we also introduced agriculture. So we are different than other organisms where we're able to raise livestock, domesticated livestock for food, and we also raise crops. So land use change is required for human civilization. So through the process, we're going to have to do some deforestation, so cutting down some trees as well as burning forests. And these are anthropogenic processes that ends up removing vegetation and releases carbon into the atmosphere. So we have a little CNN clip about deforestation here. And then just in generally speaking, when we change land and change it for human use, we are taking carbon from the biosphere and releasing it to the atmosphere. So when rainforests and other types of forests are originally carbon sinks, sucking up more carbon dioxide than they release, we turn that land that was a carbon sink into a carbon source by turning it for human use.
Leaves the balance of humanity and the balance of the planet poorer and more impoverished. It's a short-term economic gain that benefits few at the expense of the many. Deforestation is the practice of cutting down forests for various different reasons, but it's fundamentally cutting down trees and leaving behind a vast open wasteland. Deforestation is most common in countries like Brazil, Indonesia, and Mexico, Papua New Guinea, and Russia. The main causes of deforestation can be classified into three categories. Basically, industrial uses, chopping down the forest to build factories or to build residential areas. The second one is agriculture, so cutting down forests in order to grow, for example, palm oil plantations. Agricultural deforestation can also be caused by non-food crops, for example, pulp and paper plantations. And the third cause is livestock. So in many places, for example, in Brazil, deforestation is caused by farmers clearing the land to create pasture land for cows. Deforestation can happen on a lot of different scales. It can be anything from illegal squatting, a dozen folks in a local village using small rudimentary chainsaws and cutting down the trees. And then, of course, on the other end of the spectrum is massive industrial scale deforestation, where they bring in lots of heavy machinery, very advanced technology, and they can go in and clear forests in a very short amount of time. Deforestation affects the environment in two main ways. Trees, of course, absorb carbon dioxide, and as human beings put more and more carbon dioxide into the atmosphere, the more trees we cut down, the more we hinder the ability of the planet to balance how much carbon is in the atmosphere. But another impact of chopping down forests is, of course, reducing the habitat for animals to live in. Every year, over 1,000 different species go extinct around the world. That is a conservative estimate, and a big chunk of that happens because of deforestation.
Our next process is sedimentation and rock formation. So weathering of rocks and organic remains will introduce carbon into the hydrosphere, and it breaks it down into sediment. So for example, sediment turns into rock over millions of years with heat and pressure. So calcium carbonate rich shellfish become sedimentary rocks. So we have the picture on the bottom here. We have shells from our shellfish, and then it's made out of calcium carbonate. And if you remember from our ocean acidification, it gets that carbonate from the hydrosphere. And then when they die, their shells will sink to the bottom of the ocean. And then the water, because it's moving all the time, will break it down into sediments. So if you look closely at sand on the beach, you might notice that these are tiny little pieces of shell. And the sand and the shells will just keep on breaking down, and eventually it's going to get buried with other layers of sand, dirt, and so on, sediment. So generally speaking, it takes hundreds of millions of years for this to happen. And then as the layers increase, a lot of pressure and heat will compact it and turn that sediment into rock. So one of the most common types of sedimentary rock is limestone, which you see in the bottom right here. That is pure calcium carbonate. So biomass from vegetation buried over millions of years will turn into energy-rich fossil fuels buried deep within the geosphere. So sedimentation, the death of phytoplankton, also through sedimentation will become our fossil fuels with after being buried for hundreds of millions of years and heat and pressure. So these two processes take carbon from the hydrosphere and stores it into the geosphere. So our next process is combustion. So this is another anthropogenic source of carbon. So we have a general equation, but here with octane reacting with oxygen to produce CO2, carbon dioxide, and water. So octane I used, but in general, any hydrocarbon, which as a reminder is a molecule with both carbon and hydrogen. So since the late 1800s, so that's back during the Industrial Revolution that was taking place in North America as well as England, humans started harvesting more fossil fuels from the geosphere to produce energy via combustion, a process that releases CO2 in the atmosphere. So during the Industrial Revolution, we invented combustion engines to power our trains as well as steamboats and so on. And that allowed humans to have a large scale commerce and globalize, and that requires a lot of energy, which is what prompted mining as well as drilling for fossil fuels. So as global energy consumption rises, we need more energy. And the only way to get more energy is to either have renewable resources such as solar or wind, or you could do water power, hydropower, or we can resort to non-renewable energy, which is drilling for fossil fuels. We are at risk of depleting these non-renewable energy sources since we end up using fossil fuels a lot faster than they can form. So we've been burning through our fossil fuel reserves within the last few hundred years, whereas if you remember from the video from part 1, that fossil fuels takes hundreds of millions of years to form. So this process takes carbon that was stored deep within the geosphere for hundreds of millions of years and releases it into the atmosphere as CO2. All right, so last but not least, we have the air-sea gas exchange. So the process of dissolution is when atmospheric CO2 dissolves into the hydrosphere, and some of the dissolved CO2 can return to the atmosphere through diffusion. So essentially what it means is if there's a gas over liquid water, some of that gas can dissolve into the water, and it depends on what we call the partial pressure of each gas, or how much of each gas is there. So dissolution takes gases, CO2, from the atmospheres and dissolves it into the hydrosphere, so that forms dissolved CO2. Dissolved CO2 becomes carbonic acid, and carbonic acid dissociates to create hydrogen ions and bicarbonate ions, which can further dissociate into carbonate ions that shellfish use. And diffusion is the opposite direction. So the CO2 doesn't stay dissolved forever, is that some of that CO2 can go back into the atmosphere. But in general, there's more dissolution occurring than diffusion. So as CO2 levels rise, more CO2 enters the ocean, which helps reduce the effect of climate change. So as mentioned before, the ocean is a major carbon sink. There's 50 times more carbon in the ocean, so it buffers the effect of excess CO2 in the atmosphere. So the ocean is doing a great job right now of preventing the temperatures on Earth from rising too much. However, as we have excess CO2, the amount of CO2 climbs, that could lead to ocean acidification. And then in that lesson, we talked about how the shells of shellfish as well as coral dissolve and they become weak. And that's going to negatively impact the marine species. They're going to be more vulnerable and more likely to die. So whenever that happens, you're going to impact the food chain within the oceans. And another thing that's occurring is that as more CO2 is in the atmosphere, it is warming up the oceans as well. And if you warm up the oceans, less gases can dissolve. So actually the rate of dissolution will become lower if we increase CO2 emissions in the atmosphere. All right, so on this slide, we're just going to talk about the overall human impact on the carbon cycle. So here are some facts that I found on the web. So global average growth rates of carbon emissions have been 4% since 1990, so about the last 30 years. And locally, much greater growth rates, 50 to 100 for developing cities and power plants. Uncertainty at a continental scales ranges from 5 to 20% per year, and uncertainty at process-relevant scales, individual cities and power plants are as large as 50 to 100%. So essentially what that's meaning is that we're increasing the amount of carbon that is in the atmosphere, and that has large-scale implications for the carbon cycles and affects the other processes.
The Earth's atmosphere is a mixture of gases. Some are known as greenhouse gases. That's because they trap heat from the sun and warm the Earth. That's good, because without greenhouse gases, our planet would freeze, and life as most of us know it would be impossible. These greenhouse gases, mainly water vapor and carbon dioxide, naturally cycle between the land and atmosphere and ocean. And over the ages, these greenhouse gases have reached a delicate balance that results in temperatures that we like a lot. It's been that way for thousands of years, until the last 150 years. That's when people began burning fossil fuels. Those fossil fuels, coal, oil, natural gas, contain carbon that's been locked away from the natural cycle for eons. But when we burn them, that carbon joins with oxygen to make carbon dioxide that goes into the atmosphere. It throws the natural balance out of whack. The more carbon dioxide in the atmosphere, the more heat that is trapped, and the warmer it gets. And the warmer it gets, the more the climate changes, and the higher the ocean will rise. The more we learn about carbon dioxide and other greenhouse gases, the better we can deal with the changes caused by global warming. Because good planets are hard to find.
So we want to talk about why is it a bad thing that we're adding more CO2 into the atmosphere when photosynthesis can bring it out. So we want to talk about something called carbon neutrality. So carbon neutral refers to processes where there's no net change in atmospheric carbon, whereas carbon positive adds more carbon to the atmosphere. Last but not least, carbon negative processes removes carbon from the atmosphere. So in the biogenic carbon dioxide cycle, we have a beautiful natural process where trees will take in the carbon dioxide from the atmosphere, and then it makes oxygen for all the organisms on Earth, and then organisms and the trees themselves will respire and release CO2 in the atmosphere. But as we mentioned before, photosynthesis occurs at a higher rate, so there's more CO2 being absorbed by the ocean, by the forest than it is going to be released. So that is a carbon negative process. That's why we call the forest carbon sinks. However, whenever we have something like burning of fossil fuels, that is an anthropogenic or non-biogenic source of carbon. This is what we call one-way carbon cycling. This is a carbon positive process because there isn't anything that we have invented to counteract all the CO2 that we are releasing to the atmosphere. We are burning way more fossil fuels and releasing more CO2 into the atmosphere than is returning back into the geosphere. So this becomes an unbalanced act where there is more emissions through human changes on Earth, more emissions of CO2, and we're not canceling it out. And that's why CO2 levels are rising on Earth. So here we have this image from IPCC that dates back to 2004. So these numbers might be a little different overall, but just generally speaking, fossil fuel burning and land use will release about 29 gigatons per year into the atmosphere, and there's nothing counteracting that really. So vegetation and land, so we talked about our carbon sinks. It's going to take in 450 gigatons of carbon and it releases 439 gigatons of carbon. So there's more carbon being taken in than is released. And then the oceans, once again, 338 gigatons of carbon being dissolved into the oceans, 332 being released. So that is also a carbon sink. However, as humans continue to burn fossil fuels, this is going to throw the carbon cycle out of whack. So instead of keeping the atmospheric CO2 levels low, we keep on adding it to the atmosphere without removing it, which is what's resulting in the greenhouse gas effect and leading to climate change. So some of the key takeaways from this lesson are as follows. So carbon is cycled through the four spheres via naturally occurring biogeochemical processes. The majority of carbon on Earth is stored in the geosphere via the rock and fossil fuel formation. These processes will take millions of years, and that keeps carbon out of the carbon cycle, so low amounts of carbon that is cycling. And forests and oceans are valuable carbon sinks, removing atmospheric CO2. And the biogenic carbon cycle is carbon neutral, keeping carbon concentrations in each sphere relatively stable. So without humans, Earth can take care of itself. However, anthropogenic factors, our human factors, are introducing more carbon into the atmosphere and disrupting the carbon cycle, resulting in rising atmospheric CO2 levels. All right, so with that being said, thank you for finishing parts 1 and 2 of our video presentation. Let's talk about our assignment for session 8. So our assignment is going to be the carbon cycle poster. So the directions are self-explanatory, but you get to work either by yourself or in groups of up to 4 within the same class to create a poster of your choice. It could be digital or it could be a physical poster in person that you take a photo of. And that's going to be due this upcoming Sunday on the 25th at 11:59. At the end of these slides, there are a few examples of carbon cycle posters. Please note that the values that are found in these examples may either not even be represented or they might not be accurate. And the reason being is that a lot of these carbon figures, the numbers that you see that were in my slides, vary based on when this data was collected. So the rate of carbon entering the atmosphere may be different now than it was 10 years ago. So please be consistent about the numbers and just rely on the numbers found in the slides. So thanks for listening. We'll see you next week for our next lesson.